Yeah, last but not least, I would like to show our results from modeling eddy temperature fluxes in the Labrador Sea, actually. So why do we do that? So we know for quite some time that our global world ocean is not like very quiet, but rather an ocean of eddies and a lot of vortices and dynamics. And we saw similar figures like thousands of times in the last 3 days, but I would like to remind ourselves that behind such a rather theoretical thing like this energy spectrum, there are actual physical like processes behind. So for example, this very nice recently published compilation of Dong et al. It's a 1 terabyte data set of global observations of eddies. So go on the internet, download it and analyze it. I think it's very valuable. And what you see on this exemplary plot of them is that those eddies actually do something. So here, as an example, they change the density field. And from my understanding, if you change the density field, you change everything and also affect climate. So it does matter what we do here, I think. And to be more specific, studies could show that eddies also affect the structure of the mixed layer depth and pycnocline depth. And this is of particular importance in respect of climate, because mixed layer depth dynamics are associated with the formation of deep water masses. And those are in turn like an important constituent of the global circulation structure, which is then again a very important component of climate. So I think it's really important. And also very interesting are those reviews, because it's not only affecting those physical dynamical component, but also the biology. And it was also mentioned yesterday, and I want to stress it again. If I change, for example, the nutrients for phytoplankton and all that stuff, I change the carbon uptake of biology in the ocean, in fact, affecting climate again. So, yeah. So these have in common that they are all, I would consider them as observations. And what we do now is to use a realistic ocean model and check if we can actually model this or similarly. How does it look like? Maybe it looks like that in the model. So those colors show this Rossby number, which was also seen again the last 3 days. And where the colors are rather bold, like the strong red and blue, the Rossby number approaches 1, which already explained that it's like our threshold for those mesoscale, sub-mesoscale dynamics. And however, how it's also looking like in state-of-the-art climate models is rather like on the right-hand side. So you see all those vortices are suddenly gone. So what really matters here from the numerical model perspective is the resolution. So here I show in colors the resolution in kilometer of a realistic ocean model that we use. And as you can see, the resolution is highly irregular. And we followed some principles here to increase the resolution in areas where we think we should to capture important dynamical processes. So for example, on the right-hand side, this low resolution mesh, you see very nicely that along the equator, as well as along the continental slopes, we increase the resolution to capture important dynamical features as upwelling or also Kelvin valves. And then coming back to this mixed layer dynamics, the Labrador Sea here to the on the western side of Greenland, and also Irminger Sea, east side of Greenland, are known to be important hotspots of deep water formation. And if you remember the pub quiz, this is so important that we even got asked in the pub quiz, where are these areas, right? So, and then on the left, on top of that, we increased the resolution in the whole North Atlantic with respect to some rationales. I explain this now. So this ocean model is called FESOM that we use. It's FESOM 1. So meanwhile, there's already FESOM 2 released and used widely in many applications, but we have still this version 1 and it works quite nicely. So as I said, on top of this low resolution, we made this high resolution mesh to really examine the effect of the horizontal resolution on climate. And as you can see in those 3 points here, we additionally increase the resolutions in areas where we observe high SSH variability, large temperature gradients, and also steep slopes. So I find that very interesting, and also in contrast to the concept of Brüggemann, who presented today earlier. I find it nice to have like different approaches. And what we did were classical so-called hidden-cast experiments. So since this is an ocean-only model, we need to force this model, and we did this with a very classical core 2 forcing. And this core 2 forcing ranges from 1948 to 2009, so 60-something years. And we did this for 5 cycles, because as you know, at first you start this model from scratch, like from some initial condition, and then the model needs some time to equilibrate and find its own equilibrium. The typical protocol is, since this forcing is limited to this 62 years period, is to repeat those cycles. So you start from initialize, and then you run to the end, and then you take the last output and initialize the next cycle. And we did this 5 times, which is pretty much standard protocol. So if you want to know any details, I put the links here. If you downloaded, all those blue things are links that you can click on. And then one important method point I would like to make here is how we define our Eddy signal, actually. So the first aspect is the spatial component, and we simply do this by our high resolution in a spatial sense. And then the second, which is that we apply the classic Reynolds decomposition. And this seems to you maybe as a very trivial fact, but I will need to come to that point in the end. Again, so we define our, so in the next, I will show some results of those eddy temperature fluxes. And as you can see, to compute them or to obtain them, I need to save somehow this product here of the velocity field and the temperature. And we did this, we calculated during the model run, we calculated this first part of the right-hand side and saved it monthly wise. So for every month, I have like then the integrated signal of this product. And the left-hand side is then in the end the eddy temperature flux. And with this definition, our eddy temperature fluxes represent signals on the temporal timescale from the model time step to a month. Okay, so it seems very trivial, but in the end, it will become important again. So the results. So in the next, I will show you a very simple temperature budget in the Labrador Sea. So again, the Labrador Sea is like to the west of Greenland. And as you can see, this budget that I show you is pretty simple. So I show you the depth tendency equation of the depth integrated temperature. And there are only a few parts, namely the advection and the forcing and the rest. So as you can see immediately, the rest incorporates a lot of signals because all this diffusion stuff, vertical parameterization, non-local effects, all is in the rest. So the rest matters definitely, but it's already very interesting to take a look at the interplay of the forcing and the advection actually. And what we chose the flux form of the advection here, which incorporates also the Helmholtz decomposition, which we heard, what we heard several times beforehand. And to put it with my own words, as I understand it, we split the whole velocity, the vector signal in a rotational and a divergent part. And now in the rotational part, imagine you have like an eddy that transports temperature like around, then this rotational component is actually pretty large. But if I ask you, yeah, what is then the effect of this eddy? Then I think there's not any, because the temperature arrives again on the same spot. So, and to better distinguish between those, with this flux form, we get rid of the rotational component and only taking a look at the real converging and diverging signals. So really the signal that really changes the temperature on a location. But as I understood, there are many different views on this Helmholtz decomposition, so it's good to learn things. So what I show here on the left is like the low resolution and high resolution model results of the forcing. And you will see in a second that the colors here, this greenish colors, is negative everywhere, which just means that temperature is removed by the forcing on average in this Labrador Sea, which is well known. Nothing surprising here. So then you can see this red contour here. First, very huge on the low resolution and much smaller in the high resolution. And this is just some isoline of the winter mixed layer depth. And in comparison, you see this dashed magenta one, which is just a observation of the same thing. And the key point here is just that in the low resolution, this mixed layer depth is way too large, way too deep. And this is a very common problem in also state-of-the-art climate, also coupled climate models. It's not only ocean only, but also coupled, also of the current CMIP6 cycle. It's really a problem. All those models show way too deep and bright open ocean deep mixed layers. And as you can see in the high resolution model, this red line, the area of this red line is way reduced and fit much better to observations. But I will come to that in a second. First, I would like to show you now the result of the advection terms of the temperature. And now in the mid row, you can see the mean temperature convergence, and in the bottom, the Eddy temperature convergence and divergence. So again, the positive, so like yellow, reddish colors means that locally temperature has increased by this component, and this greenish, bluish, the opposite. And as you can see, the boundary current, which comes here like along Greenland and then Labrador, like transports a lot of temperature signals, and it's in a low resolution model, this current is much broader, and the structure is much more homogeneous compared to the high resolution one, where we see a lot of small scale structures. And the key point here is that in the bottom, if you compare like the absolute numbers on the bottom with the mean convergence and the Eddy temperature convergence, you realize immediately that they are much lower. Also, not only in the low, but also in the high resolution model, actually. So if I now, since we are interested in the dynamics of this mixed layer variability, and since we have this very nice long integration of this high resolution model as well, now you see a time series of this temperature Vj in the Labrador interior. And I would like to focus on the I'd like to ask you that you focus on the bottom plot, and there on this magenta line. So this magenta line is again the forcing. And you can see that throughout the forcing period, as we discussed already beforehand, the forcing leads to a temperature decrease in that area. And those phases here where the forcing is even stronger is associated to the North Atlantic oscillation, which is like the dominant atmospheric variability pattern in that area. And what we see very nice in this high resolution model here on the bottom is that this magenta forcing line is very nice compensated by this black line positive here. And the black line is the total advection of temperature, meaning just to sum the median, the mean and the Eddy advection components. And as you can see, the blue is the mean component and the red is the Eddy component. And there are periods where the Eddy component is very, very small, and the mean component, but there are periods where the Eddy component gets quite large, and both together are able to like balance this vigorous forcing. If you, however, look at the top in the low resolution model, that balance does not work at all. And as you can see in the black dashed line here, that the rest needs to cover to close the Vj. Okay. If we so now we can directly see the inference on the mixed layer depth. So on the top, we have the winter mixed layer depth here, and the black line. With the black line, you realize that in a low resolution model, there's almost no temporal variability, and it's the mixed layer depth is very deep throughout the forcing period. The red line, however, shows the results, the same thing of the high resolution model, and you can see that there's a pronounced decadal variability with periods of also deep mixed layer, but also very, very shallow ones. And this again is linked to the atmospheric forcing indicated by the bars in the background. And now if I integrate the temperature Vj just over this 3D mixed layer, I realize again a similar thing, that in the high resolution model, those Eddy fluxes, like the red curve, are able to push the total advection rather that it's not only negative, which is of course the case in the mixed layer if it's deep, but also to kind of compensate again. And in the low resolution model, where you can also see with the red dashed line here, actually the subgrid scale component of the classical Gent-McWilliams component is not strong enough to generate strong enough eddies or an eddy flux that compensates for the forcing. So the question is now, where do these eddy fluxes come from? And here we made a very classic approach of the Lorentz energy cycle, which is a very nice summary and can be found in this book, in this chapter. So the energy takes various routes, and in the end, we are interested what's generating or removing EKE, like eddy kinetic energy, in our area of interest. And important just here is to name that there are different aspects, like the barotropic instability and the baroclinic instability, and also the eddy wind work. So the baroclonic instability is given here on the bottom, and it's nothing else than the horizontal and vertical shear of the flow, whereas the baroclinic instability is like upwards eddy buoyancy fluxes. So the energy that lives in steep isopycnals, if you want. So, and now we do the similar thing. So again, the forcing, we can see it's positive everywhere. So meaning that EKE is generated by the forcing simply because the wind and turbulent wind and ocean surface currents are like aligned in a more or less same direction. That's why this dot product is positive, right? And then further, I show here the horizontal Raynaud stresses, so like the EKE generation associated with horizontal shear. And here we see again that the strongest signals are along the boundary current. So this is also not new. This was shown a lot of times. And also the signal is much higher or much larger in the high resolution compared to the low resolution model. And at the bottom, you see now the baroclinic instability. And here you realize that like EKE is generated more or less everywhere and also to a very high amplitude. So if we take a look again at the temporal structure, I would like to focus again on the bottom. So on the left y-axis, you see the baroclinic instability. So like this WB prime. And on the right axis, with different unit, you just see the volume integrated EKE in dashed. So if you take a look now in the temporal evolution of the solid red and dashed red line, you can see that they fit very, very nicely together. So, and again, you can see in the background that it's also like during this periods where the forcing is very vigorous, it poses strong forcing to the water column, that the baroclinic instability starts and generates a lot of EKE. In the middle, you see the horizontal on the left and vertical Raynaud stresses on the right. And you do not need to figure out all the details. It's just that those components, this barotropic instability, is of lower magnitude compared to the baroclinic instability. On the top, you see the forcing. And if you take a look at the numbers, you can realize that the forcing imposes the strongest signal. However, we do not see this. We do not see actually that, or as you can see, is that the temporal variability is not similarly aligned with these NAO cycles. Okay, so I arrived at my summary. At the 5 kilometer resolution, we could nicely show that eddy temperature fluxes become very active and restratify deep mix layer during strong forcing. However, if the forcing is not strong, these eddy components are also small. At a 20 kilometer low resolution, which is also quite high actually, the state-of-the-art subgrid scale parameterization is too weak to compensate for these missing dynamics, and the mix layer stays very deep. So in a way, our model results of the high resolution model are a very nice confirmation actually of this parameterization suggested by Fox-Kemper already quite some time ago. And nowadays it's actually implemented like that those baroclinic instabilities, like this upward buoyancy fluxes, are implemented in the model to arrive exactly at that thing, to flatten the isopycnals if they're too steep. What was kind of new in our study was that it was not shown with this decadal variability or with this decadal perspective, and also this combination with forcing. That is what we found quite interesting. My last summary point is that what was really frustrating during the study is that I felt that there are many confusing definitions of the temporal eddy signal. And I want to end with this with this slide here. You don't need to check all the details. There's just one point I want to make. So since this Labrador Sea is a very important area, we were, of course, not the first ones who did those analyses. And many studies before arrived at the conclusion that the mean temperature advection and the eddy component are actually on the same order of magnitude once you increase the resolution. But again, as I showed, this is also the case in our study, but only if the forcing becomes active. In the average, as you remember, you see it on the top right. The mean component is much larger than the eddy component in the temporal average. And what is different to those studies and our study is how they defined the temporal window of the eddy. And as you can see, in those studies, they took a very long average as 5 years, 14 years, 7 years. And then and calculated the eddy component as deviations of that very long mean. So, and I think it's intuitively clear that if you have a very long mean and then you have only one daily snapshot of it, and then the distance to that very long mean is of course much larger compared to if you have only a shorter mean. But what does that eddy then mean? On the one hand, they want to have an eddy signal on very small spatial scales, but with those definitions, they have a very, very long temporal scale. So for me, that does not really fit together. And that's why we made this other approach of how we define an eddy. And actually, this one study here, Kawasaki and Tazumi did the same. So their eddy signal is also from the model time step to 1 month. And they also said, hey, the eddy component is as large as the mean component. So how does it go together? And now I go back to my summary slide. And they used a daily climatology of atmospheric forcing to drive their ocean model. And this red bar here, like from 97 to 93, this is the period where their daily climatology drove their model. So it was a climatology over this period here. And as you can see, in this period is characterized also by active forcing, NAO+. And there also we see that eddy and mean are of similar magnitude. So what does it mean is in the study by them was kind of biased towards NAO+ state and was maybe not really representative of the typical dynamics of the general mean to eddy ratio. Yeah, I discussed this with these Japanese guys and they kind of accepted that, so they were fine with it. Yeah, okay, thanks a lot.